Unikernels allow us to specify the minimum features of an operating system we need to deploy our applications. We've had many shows about containers, which allow you to deploy your application on top of a segregated portion of an operating system. Unikernels are different than containers because they can be deployed directly to bare metal or to a hypervisor, and there are many other differences between them, which we get into in this episode. Idit Levine works on Unikernels at EMC. We had an interview a few weeks ago with her colleague, Scott Weiss, and today's conversation goes deeper into the motivations for Unikernels, the problems Unikernels solve, and the project that she's leading called Unik, which seeks to add the degree of usability and adoption to Unikernels that Docker brought to containers. Before we get to this episode, a few quick announcements. If you're interested in advertising on Software Engineering Daily, send me an email, jeff@softwareengineeringdaily.com. There are more than 14,000 engineers that listen to Software Engineering Daily on a regular basis, so it's a great place to get your product out into the ears of developers or to advertise available jobs that you might have at your company. Also, if you're an engineer that's looking for an open source project to work on, check out Software Daily at softwaredaily.com. This is an open source news and information site about software. It's being led by Jeff Tribble, a member of the Software Engineering Daily community. You can also check out softwareengineeringdaily.com, which is the website for this podcast. You can find links to the Slack channel, my Twitter account, my email. You can find a link to sign up for our newsletter, Software Weekly. And with that, let's get to today's episode. Continuous integration is so useful that I've started using it on my own personal projects. SnapCI from Thoughtworks has the fastest setup I've ever seen. I registered for SnapCI with my GitHub account, and after a few clicks, I had continuous integration pipelines set up for a Node.js application and a Rails application that were just sitting on my GitHub account. And I don't want my users to experience breaking changes, so I want to run a large suite of tests for my application every time I push a change. And SnapCI will run those tests quickly, in parallel, on a worker that SnapCI spins up and takes care of for me. Whether you have personal projects like me, or you work at a company that is looking for the perfect tool to improve the deployment process, go to snap.ci/softwareengineeringdaily. SnapCI embodies the lessons that Thoughtworks has learned from 20 years of software deployment, the same lessons that have been written about by Martin Fowler and Jez Humble. Check it out at snap.ci/softwareengineeringdaily. It would support Software Engineering Daily, and you would get to check out continuous deployment. snap.ci/softwareengineeringdaily. Thanks for listening. Idit Levine is the CTO of the Cloud Management Division at EMC. She has previously worked at several other companies focused on cloud computing and virtualization. Idit, welcome to Software Engineering Daily.
Thank you, Jeff. Thank you for having me.
Yes, it's great to have you. So today, most of our software development takes place on virtualized operating systems. What are the different layers of this virtual stack?
Oh, cool. So if you look in today at all the stack, you will see that the first thing that we have everywhere, it's the hardware itself, right? That's where the stuff is, where the stack is starting. And then you have the drivers of them, right? On top of it, you have something like an hypervisor, which is supposed to separate between virtual machines. Then you have the virtual drivers on the operating system of the guest. Then you have the operating system, the kernel of the guest. Then you will have the processors, the OS processors, that their job is basically to separate between different processes that are running on the same guest OS. And then on top of it, it depends. You can put Docker container or any container that you want, so that will be on top of that. And then usually you're putting all your library and every config application and everything you need inside. And then you have, of course, the application binary. And all this stack, it's basically, in the end of the day, showing you what you really want to do, which is to run your application.
So we have hardware drivers, we get hypervisor, virtual hardware drivers, the operating system kernel, there's a bunch more layers. Why do we have so many layers?
That's a good question. And I think that the best answer for that will be evolution, right? I mean, in the beginning, you had only the physical machine, big computer that business was running, like mainframe. They were buying it. It was very, very expensive. So then they basically say, well, that's very, very expensive. We need to run more application on it. We cannot run only one application on this very expensive piece of physical machine. So then basically, so then because of this, they will put, there is the operating system that the job is basically to separate between users and application, right? To make sure that two applications can run on the same machine, but they cannot harm each other or kill the machine, and then both of the applications will die. But then what happening is that was very hard, right? So people starting to, you need to do time sharing. Not the same people can work on the same machine at the same time. It's very, very complicated. So what people wanted to do is basically to say, okay, what if we will take one physical machine and run one application? But again, that's in terms of money, it's not really the best approach. So then came, in the evolution, they came and said, what about virtual machine? If we will put virtual machine, we can actually create another layer that will separate those servers, will give us the same ability of actually to run one application on a server, but actually it will be a several application with several virtual machines on one server. So that was the next layer. And then after it, they said, well, it's still complicated. There is a lot of configuration management you need to do to this application. You need to manage them. Very, very hard. What if we will find a better way to separate between the application and on top of the virtual machine? And this is where the container comes. And basically, the container is a very good use of, let's just deploy this application. It's like a packaging tool, if you like. So that's when the last container layer kind of came. So all this one is basically just evolution, but they never kind of stop and say, well, is that make sense? Or maybe it's not make sense anymore. No one did that, right? They basically continue to build up what exists. And therefore...
And so when we do take a step back and we say, do we actually need all of this? Do we need all these layers? Is there unnecessary redundancy in this stack? What is the answer to those questions?
For my opinion, there's definitely no, there is not. I mean, I feel that all those layers are abstraction. There is a lot of code. There is a lot of dependency, a lot of stuff to reason about, and I feel that this is a lot of unnecessary. Today we're running application, usually one per server. Sometimes we're running only function, right, with Lambda and other serverless technology that exists today. You don't need all of this. It doesn't make any sense to use it, and therefore I think that it's just overkill, and that's what makes it more complicated, less performable, a lot of storage that you really, really don't need, and you still put the bit and the byte. So basically, I really don't think we need it.
So the aim of the current stack is typically to run a single application with a single user on a single server. How does the aim of the current stack, how does this contrast with how we are actually building and running applications when we think about it from a fundamentals perspective?
So we are running eventually one application on a server user. We are doing it. The problem is that when we're doing it, that's the end result. This is the interface that you're putting the application in the end, but there is a lot of very complicated stack before. And it's influenced the ability of the application to be very performable. So eventually we are doing it, and basically the reason we're doing it is because we created more and more layers eventually that will give us what we really need, which is to run one application. The only thing is that if one will take all this layer and say, wait, can we actually take all of this stack and just, rethink about what we really need in order to run it? And, clean it up, clean slate, you probably will not choose this architecture. It is going to work. It's just not the right one. It's not the best one. It's not the more efficient one.
So you have said that in our current model, we are trading off efficiency in favor of compatibility. And you've touched on this in this conversation already, but I really want to give the listeners a better idea. Describe what you mean by these trade-offs between efficiency and compatibility in more detail.
So what I mean is that when you today want to run an application, you want to do it usually on the current machine, the current operating system, the current machine. You probably don't want to take your operating system and run it on a, Pentium 1 10 years ago hardware, right? You probably don't want to do that. But if you will take right now the distro of an enormous operating system that you want, and you will try to do that, you will be successful. You can actually take right now, Debian distro like Ubuntu and put it on 10 years ago computer. And the question, why? So basically, when we are creating this evolution about let's go and add more, make the stack better to run one application with the one user on a single server, it was important to us that in order to make it adoptable, we will support the old architecture. And when you're doing this is fine, but then you basically cannot make it. You have some dependency and limitation. You cannot do it the best or the most efficient that you can. So what I'm saying is that the community of the operating system basically make a choice. And the choice that they make is that it's much more important to them to run, to support all the old architecture, probably because it's easier to make it adoptable that way than to actually, start with a clean slate and say, what do we really need? And that's what I meant. I meant maybe the best approach will be let's just think about what we really need in order to run the application of today, because the requirement change.
So in what ways does the Linux kernel have excess complexity? As we've built up these additional abstractions, as we've built up this additional compatibility, where are the most pertinent places where we have excess complexity?
So the first thing, first let's separate between the operating system itself and the layer that we put on top of it, right? The kernel itself has a lot of unnecessary, for instance, driver that you can run with, right? If you're going today and you're running on the cloud, you cannot go to the machine, you're still going to have a USB driver. And the same thing with floppy. No one is using floppy, it's going to be there. And there's a lot of other examples of stuff that you don't really need. Maybe you run an application that's not even using the network. You're still going to have the network driver. Or you don't need a volume. You're still going to have the volume driver. So basically what I'm saying is that you have a lot of stuff that are necessary. This is the first complexity because, this is lines of code that you need to maintain, that you make sure that it's working and supported. The other thing, if you have all of this line of code and complexity, for instance, before, when you were running, you ran on these big machines, therefore you had more than one user. And because of that, you need to make sure that you check, there is a permission check, right? You need to make sure that me as a user are not doing any harm to your application. That's, again, not necessary if you only run one user. And in the cloud today, that's what we're doing. We don't really, you're running the application. You can have a multi-users on the application itself, but you don't really care on the level of, of the operating system itself. And actually, it's also not secure. I prefer that no one will be able to actually SSH to your machine. It's dangerous. So that's another thing. All the permission check, it's also, it's taking your performance down, right? Because the operating system actually need to check before it's doing something.
You define what a permission check is for those who don't know?
Yeah, permission check means it's basically, the question of, so you have so there is a few things. First of all, permission check is who is this user, right? And second of all, there is two layers on the operating system. One of them is what called kernel mode and user mode. When I'm running application, I'm running it on a user mode, and the only thing that is running on the kernel is basically the operating system itself, the kernel itself. So if I'm making a call in my operating system, what will happen on my application? Usually, I will have some libraries that I'm going to use that will make what called an API call to the operating system. When that will happen, it will go to a kernel mode, right? Basically, the kernel will catch it and say, is that okay? Are they writing to a place that I'm okay with to write to? Is that not violate any of the permission check? Maybe he's writing to a place when there is another application using in this memory, right? So just make sure that this is a safe call. So that's one thing that I mean. So first of all, who is the user? And second of all, make sure to separate between user and between application and user. Does that make sense?
So explain, yeah, absolutely. So explain why this model of permission checks is somewhat outdated and why it penalizes us so much.
Mainly, it's not needed right now. If I'm using, and I'm running, as we said in the beginning, the purpose is to run one application. So there is no virtual, it doesn't have to have a virtual memory, right? Sorry, a virtual space address, because there's only one application. This is, the memory is what we have. And therefore, there is no, there's not going to be any problem with a page fault, and that's it. Because you don't care because you only run your application. That's the only thing on your machine. If you're the only user, of course you're allowed to do this stuff. You're running on privilege mode. There is no one else. You are the only person in the machine, and this is your application. You can do whatever you want. So there is a lot of just unnecessary. It's not that it's It's very, very complicated maybe, but it's unnecessary, and that's taking a CPU cycle and so on that you really don't need to waste.
So what is a unikernel? How can we move this conversation towards a discussion of unikernels?
So the idea with unikernel is just a change approach, right? What we said is that until now we went into the evolution and we looked at what happened, we created this enormous stack. And what unikernel approach saying, let's start from the top. Let's understand what we really need to run. So you're taking your application, and now the question is what your application will need. So what libraries it's using, which driver it's using, where do you run? Are you running on this hypervisor, on that hypervisor? You're running in the cloud? All of these questions are important because, to be fair, I don't need on this machine all the drivers. I only need the driver that actually will be used. So what they did, they basically come to a different approach, and they said, here's my application, here only the libraries that I need, here is all the driver that I need, and that's it. Now package it and make it a virtual machine or a bootable image, right? So that's basically the idea. It's a different approach. And now suddenly from having a distro, I don't know, like the Debian distro last I looked was a 419 million line of code, suddenly you have, I don't know, a very small one, like 2,000 line of code. And when you have that, now it's very, very easy, right? The performance is very, very good. But also, it's very easy to understand what's going on, very easy to work on, very easy to maintain. So that's the benefit of it. But it's doing the same thing, right? In the end of the day, you're running one application in the cloud, and everybody's using it. This is like that simple, right?
When we strip away those 400 million lines of code that we don't need, and we were left with the 200,000 or 2,000 lines of code, whatever it is, what are the things that we always need? What are the aspects of that Linux kernel that we're always going to need, even though we're running in a unikernel?
So the first thing that you need is the driver itself, right? Because that's what will talk to your hardware. So you need to know that. So again, only the drivers that you need. If you don't need a network, you will not have a network drivers. The second thing that you need something to package it and manage it. That's, for instance, right, you look at something like Rampant, that's what they're doing. It's basically another like layer that will, manage that, which is, again, can be very thin because there is not a lot to manage now. And then on top of it, you have to have your libraries that your application needs, right? So if it's libc or something else, you need basically the libraries that your application code is using. And then you need your application code. Application runtime, of course, but that's it. That's all you need. You don't need much more than this.
So is a unikernel still considered an operating system?
It's an operating system in a way. It's a kernel, right? And it's people like to say that the unikernel is the application. So, but in the end of the day, operating system is something that manages it. And it is being managed, right? I mean, there is something to manage it. It's just a very, very lightweight operating system.
Mm-hmm. So my application is always going to need these certain specific things, like specific language runtimes, specific hardware drivers. How do I determine which of these is going to go into my unikernel?
So when you're running, so So in terms of the driver, you need to know where you're running on. For instance, I'm running on Zen, so I will need the driver for Zen. I'm running on, I don't know, on Google Compute Engine, so I know that what they have is basically KVM, so I will need those drivers. Or I'm running on EXSI, I will need these drivers. Or I'm running on bare metal or Raspberry Pi, it doesn't matter what. You need the driver for that. So that's something that usually it's something that the user need to do before we created our project. Person need to understand, I want to run there, this is the drivers that I need, and you need to give them. Besides that, there is the wrapper itself, and that's been given by, it's called, like for instance, in ramp kernel, it's called ramp run. This is the tool that's doing this magic. And it's also, so that's for instance, in ramp run, but there is other, like in OSV, it's called something else, and in Mirage, it will call something else. But the idea is that there is something that you that know how to build, and what it's doing is basically package it with your compiler. So in the end of the day, what you're running is binary. So if you wanted to compile application for whatever, Python, for instance, in the end of the day, what library to take from the Python, that's the compiler of Python ought to know to do. So at the end of the day, we'll take what the compiler is given, which is a binary, plus the libraries that the basic libraries that you need wrapped with the container, with the drivers, and that's what you get. In the end of the day, you're getting the Unikernel itself.
Okay, so I specify the things that my Unikernel is going to need. What is the process? Describe the process in more detail of how, after I specify the things that, the aspects of the library operating system that my Unikernel needs, how does that get transitioned into a Unikernel that I can run?
So, I can go with you as much as detail as I can, but the idea is that there is tools for it. So you don't really do the artwork. So what you're doing is you're running some command call. Like for instance, in Mirage, Mirage compile. And then you're giving the drivers that you need. It's like a command tools that you're doing. And the magic itself is done in these tools. And to be fair, this is not something that either me or my team deal with. We created some, we modified those tools, but the tool itself did not created by my team or me. Does that make sense?
Sure. Yeah. So talking a little bit more about how Unikernels actually work, a Unikernel runs in a single address space. What does that mean?
It means that, so let's say right now, let's take it 1 second to the regular kernel. Let's say that right now I have two processes running, okay? And I have I have one memory, right? So I can do a lot of manipulation with it. What does it mean? Maybe because the processor is going to do a lot of context switch, what I can do is basically run more application and more processes that each of them think that they're getting the real virtual memory, but actually I'm managing some table that reference me to who, one, where. And I'm only giving them what they really use. So what does it mean? It means that if I have two processes, and right now I'm running on one process, and I have the amount of the memory that I have is X, it doesn't really matter, I can take another process and make him think that is using the same memory, and he has all the memory that he needs, but actually that's not really true. What I'm doing is that if I need to give it back to him, I can easily, I'm managing basically the address themselves. This is how it's working in a regular machine. In Unikernel, you have only one processor, so therefore all this table or float is going, and you just don't need it. All the pages and so on, you just don't need it. So therefore you have one memory. The memory is a physical memory, and the process is using it, and that's it. It's really getting all of it. Does that make sense?
Yeah, totally. So are Unikernels better suited to small single-purpose servers like DNS, for example, or could you fit an entire Rails app in a Unikernel? So
you can fit everything in a Unikernel, and at the end of the day, it's only your binary wrapped, right? So you can take, an old application, and as long as this application is not forking and not doing anything that Unikernel is not support, you can do that. The question if it makes sense to do that, that's a different one. But I think that what's cool about Unikernel is the fact that the boot time is very fast. Therefore, usually you will find a lot of use case like in NFV world, for instance, which is basically a serverless function. So like there is something that I want to run. It's very, very small. I want it to run only when the user calling it. So because it's very, very fast for me to boot the Unikernel, I will do that, and then we'll kill it immediately. So for instance, Lambda will be probably really, really good implementation. It can be implemented by Unikernel.
Yeah, maybe you could talk about that in a little more detail. So, Lambda is this serverless, it closely aligned with this idea of serverless architecture. Explain what Lambda is and why that makes sense in the context of Unikernels.
So the idea so today, let's say you have an application, you need to write all your lines. You need to manage those. You need to write an API for it, for someone to hit the server. And a lot of management that you need to do. And sometimes, usually you need to either package it in a container and deploy it on a machine. But a lot of the time, the only thing you want is something very simple. You want to run a very small function. And this function is really not doing much. I don't know, let's say that every time that someone is putting something in S3, I want to run something. Do I really need to actually manage a server here? Do I really need to actually take a VM, put all the right patches, my application, everything that I need, create an API and so on? Maybe not, right? Because it's kind of simple. So what AWS, they were the first that I know that did it. Actually, Iron.io maybe before them. I'm not sure. But the idea is that you're only going to spin up this functionality when you actually need it. And when the user is not going to request for it, they're not going to have anything. Like your infrastructure, nothing is running it. That's the idea. So, for instance, you want to put something every time that someone is putting something in S3. So what I want is that only when someone is going to put something in S3, is going to spin up an handler that will run my container or Unikernel and do something and then die, right? So that's basically the idea with the AWS Lambda. Just don't manage your server anymore. We're going to do that for you.
Wealthfront is an automated investing service that saves you time. As an engineer, your time is valuable. If you want to invest, but you don't want to spend significant time evaluating your portfolio and allocating assets, take a look at Wealthfront. Go to wealthfront.com/SE Daily to open an account today and get a special offer for Software Engineering Daily listeners. $15,000 managed for free when you open your account. With traditional investment services, there are many humans in the loop that are doing things that Wealthfront automates away. When you pay the commissions and account fees of these traditional investment services, you're paying for work that could be done by a computer. So don't pay commissions and account fees. Maximize your gains with Wealthfront's Set It and Forget It investment automation. Check out wealthfront.com/SE Daily. It would support Software Engineering Daily, and it would introduce you to the world of automated investing. Wealthfront.com/SE Daily. Thanks to Wealthfront for being a continued sponsor of the show. Now, let's get on with the show. So let's talk about that in more detail. So if I'm Amazon and I'm thinking about how I want to vend this serverless capability to my customers, should I architect it using Unikernels? Should I use containers? Should I use some combination of the two? What would be the different trade-offs in those different architectural ways of them implementing their serverless architecture?
So today what they're doing is they're using a container, and what they're doing, because they want to spare the time of actually spinning up the container, they're reusing container. But Unikernel can be a very, very good fit for it because, as I said, it's very, very fast to boot. It's very light in terms of size. And, if your function is, if you know that every time that someone is something putting in S3, you need to run the same function. So build the Unikernel one time and then just use it whenever you want. It will be very fast to boot. And you're getting, of course, a lot of security and the benefit of Unikernel. So I feel that probably would be a better approach. But I mean, both of them will work.
Could you contrast them in more general context? So how do Docker containers compare to Unikernels?
So the idea with Docker container versus Unik, so Unikernel, first of all, it's usually a VM or a bootable image. Docker container or not, right? It needs to run on some kernel. The kernel is something that you're sharing between all your container. What you do putting on the Docker container is all the dependency of your application, the libraries, and whatever you need to run. In Unikernel, you also need to put your drivers, right? Because it's basically running directly on, it's basically a VM, which in very, very lightweight OS is running, directly either on hypervisor or on bare metal. In Docker, you need this kernel, right? You need somehow to get this kernel. So if you're running on, let's just compare, right? If you're running an hypervisor, let's say I'm running on AWS, so AWS is running Xen. So I have, a Xen. Now I can either run Unikernel or I can run container. If I'm running Unikernel, basically, I'm just running an operating system, a VM, on top of Xen. Very, very easy, right? I mean, there is no unnecessary anything there. If you're running it on container, what you need to do is to spin up some Linux machine or some operating system, and on top of it, put your container. So basically, you have an operating system that, the Linux is a little bit, it's a kernel. It's all the kernel. You're getting all the drivers and everything you can, and then you put in the container on top of it. So that's the only real problem, right? So you basically have the problem of a much mature operating system versus a very light one. And also, of course, but Docker will put only the libraries that they need on the application.
So how do the performance characteristics differ between unikernels and Docker containers? Because obviously unikernels are fast to spin up, Docker containers are fast to spin up. So are there performance differences in terms of startup time, and are there performance differences in terms of what's going on once the container or unikernel is actually running?
Yeah, so the good question need to be how you're running a container. If you're running the container on bare metal on a very minimum Linux, of course there is less. But think if you have, just for like most of the people who are running today, they are running on hypervisor. And therefore, you're running a hypervisor. In your hypervisor, you have all those Linux kernel, right? This is, at the end of the day, they're running on kernel. And you have all the, the switches and the permission check and all the stuff that we talked about it before, right? The page fault and all of this, and context switch. And then you have your guest operating system, which is, again, it's another kernel, right? And then on top of it, you put in your container. So basically, you have 2 layers of kernel, right? If you're running Unikernel, again, it depends where you're running it. If you're running it on hypervisor, you have only the hypervisor and then a very, very, very thin operating system. So basically, again, it depends where you're running it. In terms of performance, you have less layer, it's better performs. In numbers, again, you can go and see quite a lot of, for instance, IncludeOS did an article about how their Unikernel is running based, and you can see a huge difference than regular VM and even container. It's performed very, very well. Again, it depends how many layers you have in the stack, and this is your choice, right?
Yeah. Can you describe what happens when I deploy my Unikernel against a hypervisor?
Not much. It's a VM. You're putting it up. That's it. Nothing. It's like a regular VM. You can take this and that's it.
Okay. And so the contrast between that and Docker container would be that you have to have another. Right? Yeah. Could you contrast to what would happen if you deployed a Docker container against a hypervisor?
Yeah. So first, you need to install. You need somehow to deploy a guest OS with kernel, right? So I mean, that's something that will have to happen, and the kernel will be a full kernel, right? It will be like with all the stuff that we talked that it's really, really not necessary, permission check and so on. And then you're going to put the Docker container, right? So in the Docker container, you will have the library that you need. So in the end of the day, you have another layer there, which have a full Linux kernel, which you don't really need it. You don't have to have it.
I understand. Okay. So I want to talk about what changes once we have unikernels. So once we've removed all of these permission checks, how does our world change? What speeds up? What are the advantages that we are getting?
So basically, your operating system is started, and then your application is running immediately, right? And then it's your application running. It's running on a kernel mode, which means that it's all the code that you want to do. You can do. There is no the switch between the kernel and user mode. There is no a context switch because there is no other processes, and there is no fault page because there is not. It's one single space. So basically, all of this unnecessary stuff is not happening, and what really happening is that your application is running, is using whatever it needs, and that's it. I mean, it's very simple.
Mm-hmm. And since the unikernel can run directly on the hypervisor or the hardware without being in a virtualized operating system, does this mean that we can pack unikernels more densely on this underlying substrate than we would be able to with virtualization?
So the thing is like this. Let's say that right now I'm creating a bootable image. I can run it directly on the bare metal machine, but usually in bare metal machine, I have a lot of resources. And the beauty of unikernel is that you don't need those resources, right? They're very, very small unikernel, right? They're very, very small. So you will not want to waste all this huge server that you bought. So therefore, it doesn't really make to run it directly on bare metal without some hypervisor. But if you're running it on Internet of Things, embedded device, now it actually makes sense because, first of all, there is not a lot of space, and space are very, very important. And you want to give the space to your application for real and not to your operating system. So that makes a lot of sense, right? So as I said, it makes a lot of sense in this world of Internet of Things. But then what we're doing, for instance, is we're making sure that the unikernel will run directly on the embedded device, right? There is no hypervisor, there's no another layer. It's like it's streamed down on the embedded device. But if you're running the server in the cloud, I will argue that you probably want to put some hypervisor because otherwise you're wasting a lot of resource.
So is there a particular type of hypervisor that the unikernel typically runs on?
So when we started this process, most of the unikernel started in a project that called MiniOS, which is coming from Zen. But since then, we help and a lot of other and added support for a lot others. So right now, for instance, specifically, we are supporting in a EXSI, which is the vSphere environment of VMware. We're supporting Zen, just supporting KVM and QEMU. So basically, you can run on everywhere. I mean, the only thing that we are not working on yet is Hyper-V, and the reason is because it's Windows-based, and it's closed source, so we need to figure out what to do there. But yeah, it can run everywhere.
And does it matter? Are there advantages that particular hypervisors can give to the unikernel running on it?
I don't really think. I mean, I think that in the end of the day, it's a VM. So for the hypervisor, it's a VM. There's no difference.
I see.
Yeah.
Okay.
As I said, the thing that I think that it's very, very important to the VM, to the unikernel itself, is the fact that you're getting performance of container, right? Because it's even fast. Sometimes it's fast to boot it than a regular container. But you're getting the maturity of VM, which is great, right? Because you're getting the security of the VM and all the management that all those hypervisors are giving you for years. So I think that make it a very strong case. And also, people doesn't need to change anything in their environment, which I feel it's very strong. Most of the people that running today running on hypervisor in their data center.
Right. So you've mentioned security. What are the security vulnerabilities of the Linux kernel that unikernels can help give us a better model to deal with?
So I will argue that the only one is that because there is a big Linux kernel, it's a lot of line, it's a lot of functionality. Therefore, there is a lot of there is a lot of point that you can penetrate to it, right? And I think that this is the scariest things, right? I mean, you can SSH to it. You can run, you can try to mimic different drivers to create a lot of the mess on the OS. There is a lot of stuff that you can do there that is very, very dangerous. So by stripping down the operating system and taking out stuff like SSH and so on capability, you're basically limiting the surface of attack. And I like to look at it, like a good example that I like to give. It's like basically a house with the windows and the door, and you're locking them, right? So it's kind of safe, but people can still penetrate, versus a room without door and windows. So it's very, very hard to penetrate. So that's the difference between Unikernel and a regular Linux operating system.
Right. I have read also that there are certain security vulnerabilities that might be picked up if you are using a unikernel. For example, because the application is running in the same address space as the kernel, there's potentially buffer overflow vulnerabilities. Is this a realistic problem?
So, I mean, this is funny because we had a long discussion about it to try to understand what exactly, the vulnerability. I feel that what people need to understand is that eventually your unikernel is basically a VM that's running only one application. And if this application, someone managed to somehow get to the unikernel and sabotage it, the application is not going to work and the machine is not going to work. And I don't care because, I mean, I do care and I will need to fix it and spin up a new one. But it's not that I'm attached to the specific OS. It's not that I have to go and figure out what's going on because nothing will be affected except this process. And a lot of the security work that's been done in Linux is around the fact that usually you have more than one processor, and you need to make sure that if one of them manages somehow to sabotage and get to kernel mode and not do a lot of damage, it will not hurt the other. And therefore, you need to do the separation between the modes and so on. That's not clippable for unikernel because there's only one process. Therefore, if this process is, if this unikernel is dead, it's dead. It's not sabotage any other application that's running somewhere else. And I think this is the beauty of it.
Yeah. So can you contrast that with? So what what are the types of problems in the traditional Linux kernel? If you had access to the complete address space by way of this buffer overflow vulnerability, and if you had the complete Linux kernel, how would that contrast with the situation that you just described, where in the unikernel, if you can have access to the entire address space, it doesn't actually, you're saying it doesn't actually matter because the unikernel is so restricted in its functionality. Could you contrast that? Why is it a problem in the full Linux kernel and it's not a problem in unikernels?
So let's look right now. What we can do is an exercise of understand what is in the Linux kernel actually protect you. Okay. So the first thing that there is like privilege separation, right? But again, there is no need here because there is only one process running. So you don't need to say, there's no point, right? What is to separate? The second thing that will be is the protection of the rings, right? But again, there is one application. So even if this application for some reason will try to do something very malicious to the VM itself, the machine will die. But again, it's not going to affect anybody. If you're looking at protected memory space, so again, because there's only one process that's running inside the unikernel, and there's not only one single address space, right? So memory space protection guard, like virtual process, process address space from another process. There is no, again, with only one process, there is no need for this isolation. It's not really an isolation that is capable, that it's needed. If you're looking at the namespaces, again, it's the same thing. It's like there's a single process. It doesn't make any sense. If there is a fine grain of access control, like SE Linux, again, it's the same thing like the number one. One doesn't make much sense. But what I will argue is that if someone will go inside and will manage to run a buffer overflow, the results will be exactly like the results in a regular VM. But it's not going to be worse than this. Okay, you will lose the machine, which means that you lose the application. But you know what? You have only one application running on it, so at least none of the other got affected. Again, like we can continue and going, but basically application execution enforcement, again, I mean, it just doesn't make sense when you're looking at one process running in one machine. All of these things that the Unikernel is giving you, that the kernel is giving you, it's just not needed when you're running only one process on one user space. Does that make sense?
Yeah, absolutely. So, Will, do you think public clouds like AWS or Google Compute, are they going to host unikernels? How could you see that happening?
So that's a great question. So today, if I'm running in AWS, and we are, right? I mean, specifically the tool that we created called Unik is running in AWS, is supporting it. But we are limited because when we wanted to actually add the machine itself, the bootable image, to an instance, the minimum that we can get is 1 gig. This is like the minimum that you can get by AWS. Therefore, if I can run something like 52 meg, I still need to pay for 1 gig. Doesn't really make sense. So AWS is not right now the best cloud to run Unikernel. There's other cloud that more makes sense. I think, if I remember correctly, in Google, there is 2 ways you can do it, either like this, like, fixed price based side, or you can do it, more like custom. EMC has a cloud that called VirtuStream that they have like a pattern of something that called micro VM, which is basically you're paying only for what you're using. So it's but I'm assuming that when it will be more popular, they will adjust the price. They will have to. So I believe that in the future it will be more make sense. Today, probably, if you will run on-premise, it will be more usable. Does that make sense?
Yeah, understood. So you mentioned Unik. Let's talk a little bit more about that. What is Unik?
So Unik is basically, you remember that we talked about how you actually build a Unikernel? So I described a little bit, and of course I abstracted, right? I didn't tell you all the details because it's too complicated. But in the end of the day, the bottom line is that it's complicated. And what we wanted to make sure is that if there is a user that understands that he has an application and he wants to run it, and he understands that it's, Unikernel maybe is a better fit for his application, I don't know, because he wants space to, because it's more secure, because it's taking less space, because it's very performable. What we wanted to make sure is that it will be very, very easy for him to do that, because not everybody that's writing application, running, a website, understanding how to compile drivers. So the idea with Unik was, let's do what Docker did to Linux container and just make it very easy to work with. So if someone will want to go and take his application running in container, today it's not that hard to do it with Docker. We wanted to give him the same experience to run it in Unikernel. And we felt that if we will do that, people will use it because, as I said, I'm a big believer that this is the architecture of the future cloud and Internet of Things.
So how do developers actually turn their applications into unikernels today? How does that contrast with how you aspire Unik to work?
So how it's happening without Unik or how it's happening with Unik?
Both questions. How does it contrast in Unik with what's happening today?
So the work that we did, it's kind of complicated, right? We wanted to run it on EXSI. You need to figure out which driver is working on it. This is not an easy work, right? I mean, this work, for instance, been done by Yuval Kochavi, and this guy is like, that's what he knows. He's he's like debugging assembly code and crazy stuff, right? And what he did is basically, you need to understand which driver you really need there. So our luck was that RAM kernel specifically, for instance, is based on a FreeBSD. So if there is if something like EXSI support FreeBSD, we can actually go and kind of use those that if we will take those drivers that already been done for FreeBSD, it will work for RAM. So we did a lot of work on this, but it's not always work, and you need to figure out what's missing and which driver depends on which driver. So it's a lot of work that we did, right? After we did this work, now we know how to do something like that. So what we did, we basically automated that. We said to people, bring us your code. We will make sure that, we tell us which provider you want to run in. And we're going to compile your code on the language that you choose with the drivers that you need, and we'll create your bootable image. So you will not, we're abstracting all of this from you. But this is not an easy work. I mean, we worked on it quite a lot.
Yeah, there's been a lot written about, how challenging it's been for Docker to get Docker compatibility on Windows and Mac and everywhere. It sounds like with Unik, it's essentially the paradigmatically the same sort of challenge where you really have to get compatibility with all these different hardware systems, all these different cloud providers, all these different types of Unikernels. How do you address that compatibility? How do you manage that workload?
So actually, when we wrote Unik, the instruction that I had to the team is we have to make it very, very pluggable, because we don't really, as you said, right? There is a lot of providers that we wanted to support. There is a lot of Unikernel that we wanted to support. There is a lot of Unikernel special provider that we wanted to support. And to be fair, this is such a green area that we don't know who's going to win. Maybe Mirage, maybe RAMP, maybe OS. We don't know, right? And therefore, we decided not to choose, right? And what we did, we basically build a Unik to be very, very pluggable. So we've been inspired by the Kubernetes architecture. And what we did, we basically built, we kind of like created an interface to a providers, an interface to a compiler. So now if you bring me your code, there is two things that I need to know. What type of code is, like, I don't know, you want to run Go. Number two is which Unikernel you want to run it on. So either RAMP or include OS or whatever you want to run on, Mirage. And then the last one is which provider you want to run it. Because, for instance, maybe you want to run this Unikernel on Zen, or maybe you want to run it on AWS, which is also Zen. So that will be the compiler, but the provider will be AWS, right? Because when we talk into the API, we will talk to AWS. We will not talk directly to Zen. So we build it like this, that right now if you wanted to add support for something else, and a great example is probably is Include OS. So Include OS is so unique, and I read some article on it, and they said, how come Include OS is not one of these Unikernel that you support? So they just added support for it. So, as I said, it was quite easy for them, because what they needed to do is a container that will run the compile itself, and they wanted it, and that's it, because we already have the support for QEMU and the VirtualBox that they needed as a provider. So it's very easy to do that if you know what to do. So again, yeah, I mean, as I said, if you look at the code in Unik and we see how we build it, we'll see that it's very easy to extend it. Like, it's very easy to add more support to other, and we're doing it. We're doing it constantly. Right now, we're working on more and more support. So,
when you talk about RUMP versus Mirage, could you explain what the difference between those two are? Like, what is RUMP? What is Mirage? And why is this going to be? Why do you frame it as if one of these is going to win? Explain what you mean by that.
Yeah, so I mean, there is a trade-off here, right? Mirage is a RUMP kernel. RUMP run, it's basically a Unikernel that kind of supporting POSIX compliance. That means that if your application is running and certified to run on POSIX, it will work. Therefore, it means that I can take C++ applications that you wrote, or Go, or any other, Node.js, or every other language that you choose. And it's basically, I don't need to modify the language itself or the code that you wrote in order to run it on RUMP. And in Mirage, it's a little bit different, because if you look at Include OS, for instance, Include OS, the reason it's called Include OS is because you need to do Include OS to your code, to the C++ code, which means that they're using a little bit different libraries that are not the regular application is using if you're running on Linux. And therefore, what it means that you will need to modify your application. But because they build it specifically and it's not POSIX, you can get a better performance. So it's basically a trade-off. If you will run your application in Okama, which is the language that Mirage today supports, you probably will get a better performance, but you will need to run Okama not a lot of the application today is running Okama. So it's a good question based, what people will prefer. I'm a big believer that people will prefer RAMP because it's, they don't need to modify the code versus Mirage. But there is a lot of community around Mirage, less about RAMP. So I believe that eventually maybe, Mirage is going to work on adding more support for stuff. So maybe we will see. I don't know.
Great. Well, Idit, where can people find out more about Unikernels and about you and your work?
So if you're going to our GitHub, so my team is doing a lot of stuff, but that's one of the things that we did. If you're going to the GitHub EMC-advanced-dev, you can see there a project called Unik. This is where you're going to find the Unik code. You can install it and run it. It's very, very simple and beautiful. Our emails are there, so they can reach out to us. You can reach out to me at Twitter, which is Idit, IDIT, _Levine, LEVINE. And you will find me. Just Google me.
Great. And why is EMC focused on Unikernels? You work at EMC. What is the business value there? So maybe for that, I need to explain a little bit. So I'm working in EMC, and I'm the CTO of the Cloud Management Division. We basically changing the way EMC is trying to think, right? So we have something that called EMC Dojo. We're doing pair programming, test-driven development. The work look a little bit different. We're focusing a lot in Cloud Foundry and other tools. Inside this group, I pick 2 developers to work directly for me, and we're doing advanced development. So this project, Unik, is coming from that. So it's Yuval Kochavi that I mentioned before, and Scott Weiss and myself are the one who's responsible for Unik. It started as an advanced development project, but to be fair, it just succeeded more than we expected. We actually knew that it will succeed, but more than EMC maybe thought that it will expect it. And now there is a lot of use cases that we can think of that EMC can leverage that. But the main focus was, to change perception, right? EMC, as an innovative company, was doing a lot, that is head-to-head with Docker and other companies. And besides that, this is a cool technology, and this is what we know how to do, to lead. So again, there is no really business value right now, but I believe that after we did it, we discovered that there is a lot of options to put it inside EMC product, to put it inside. So there is a lot of option that we see to leverage that. Absolutely. Okay, well, Idit, thanks for coming on the show. It's been a real pleasure talking to you.
Thank you so much for having me.
Thanks to Symphono for sponsoring Software Engineering Daily. Symphono is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symphono.com/sedaily. That's symphono.com/sedaily. Thanks again, Symphono.
Wow.